Okay, recording has started, and let me present my screen. Yeah, can you see the screen in front of you?
Yes, sir.
Yes,
All
sir.
right.
Yes, sir.
All right. So let's do a review of Newtonian mechanics. As someone said last time, कि कर लेते हैं. So even though our focus is going to be on Lagrangian and Hamiltonian formulations and relativity, let's review Newtonian mechanics. I taught you Newtonian mechanics in first year. It's been some time, 2 साल हो गए. And even though Newtonian mechanics is, you know, simple compared to Lagrangian formulation, in some sense, not in all the sense. In some sense, the Lagrangian is much more simpler. But Newtonian mechanics occupies its own position and its own respect when it comes to mechanics and physics in general. The whole idea is to study Lagrangian and Hamiltonian formulation, but I also want you to appreciate the differences between the Newtonian formulation and the Lagrangian formulation. कि किस तरह से Lagrangian formulation अलग है, किस तरह से Newtonian formulation अलग था. Even though in various problems, almost all the problems, if we use both the approaches, we will get exactly the same answer, but the approach itself is very different. Even though fundamentally, physically speaking, the ideas are equivalent to each other, we can derive one from the other and the other from the one. But mathematically and the construction of how we approach a particular problem is slightly different. And so as to create a sense of appreciation for the differences that exist and the kind of things we will discuss in the coming semester, today being kind of formally the first class, let me do a review of the Newtonian mechanics that we have studied. Of course, it's a very vast subject. You can't review it in one class, but the basic ideas of the Newton's laws, the laws for point mass particles, the laws corresponding to systems of particles, conservation laws, work energy theorem, वगैरह वगैरह बहुत सारी चीजें थी. उनकी जो fundamentals है, उनकी जो basic ideas है, थोड़ा सा हम discuss कर लेते हैं in today's class. Okay. Okay, so the Newtonian mechanics or the Newton's laws or Newton's formulation all starts with a couple of axioms or a couple of laws. Okay, we will not go too much into the details because I remember first year में हम काफी detail में गए थे, looking into first law, second law, third law. But let's suppose in a matter of 10 to 15 minutes थोड़ा सा एक discussion कर लेते हैं. Let me see how much of it you remember. So there are 3 laws that essentially are in a sense complete and creates a theoretical construction using which we can look at problems, we can analyze problems, we can derive certain quantities, we can use them to predict certain quantities. So what is the Newton's first law? Like what the Newton's first law tells us?
So inertia.
Inertia, that the objects in motion tend to stay in motion, and the objects at rest tend to stay at rest.
Also the qualitative definition of force.
Yeah. Yes. Anything else? Any other additional? The objects at rest stay at rest. Objects in motion. It gives us a qualitative idea of what force is. Force is something that changes this state. The law of inertia. Anything else? Any additional statement regarding the first law? It gives us a qualitative understanding of force. It tells us what happens in the absence of forces. What do you mean by law of inertia? What do you mean by inertia?
So the point where the forces are balanced.
Sir, a resistive property of a body.
Point where forces are balanced is not inertia, Pratham.
That's equilibrium in the sense that I mean the force that the object is, the resistive force that the object is applying is the same as the outside force that are being applied to it. I mean,
Pardon?
that's how it. Uh,
Can you repeat it?
uh, I meant to say that it's the influence. I mean, sorry, sir, I'm not able to explain what I said
I
in
think
that moment.
Jishant gave the correct answer. The resistance to
Yeah,
any kind
right.
of a change in motion. In mechanics, when we say motion, we usually mean that an object at rest is at rest, or an object in motion is at uniform velocity along a straight line. When I say change in motion, anything that changes that state, anything that can make an object at rest to start moving, or anything that can make an object that is moving along a straight line to either change its speed or to change its direction. Okay, so that is a force, but the tendency of an object to oppose that kind of a change in state is known as inertia. Okay, inertia is merely a property that resists any kind of a change. सुबह सुबह हम उठते हैं तो उठने का मन नहीं करता है ना, सर्दी है, रजाई के अंदर सो रहे हैं, क्यों उठना है यार, है ना. It's very difficult. You have to really push yourself to overcome that inertia. So inertia means that you want to continue in that state of sleep, but of course you have to force yourself to come out of it. So that's the inertia you want to overcome. रात को जब सोने का टाइम होता है तो सोने का मन नहीं करता है, नहीं यार थोड़ा सा और ब्राउज कर लेते हैं, थोड़ा सा एक और वीडियो देख लेते हैं, है ना. यू वांट टू कंटिन्यू इन दैट स्टेट यू आर इन, यू डोंट वांट टू गो टू द नेक्स्ट स्टेट. So the resistance that you offer mentally, that is inertia. Yes, that is what inertia the word comes from. Yes.
Right, sir.
Yes, sir.
इसी तरह से all physical objects that move in the universe, as far as motion is concerned, movement is concerned, you know, going from one place to another is concerned, there is also a certain inertia. They don't want to change its state. अगर कोई रेस्ट पे है तो रेस्ट पे है, अगर कोई मोशन पे है along a straight line तो उसी स्पीड में उसी डायरेक्शन में वो जाते रहना चाहता है. It doesn't want to change the direction, it doesn't want to change the speed. That's some sort of a resistance that it offers, and the quantification of that resistance leads to what is the definition of mass. Okay, if we define what resistance is, we call it as mass. Okay, anything that has more mass has more inertia, anything has less mass has less inertia. However, this definition and all these discussions is only relevant to a particular inertia frame of reference. Can you name that frame of reference?
Non-accelerated.
Non-accelerated, non-rotated,
Inertial.
or more specifically inertial frames of reference. So for example, अगर आप मेट्रो में है, ट्रेन में है, बस में है, एंड मेट्रो जो है एक ही कांस्टेंट स्पीड पे चली जा रही है, इट्स फाइन, यू आर स्टैंडिंग देयर, नो इश्यूज. बट अगर मेट्रो कम्स टू अ रेस्ट वेरी सून तो आप आगे की तरफ गिरेंगे, यू विल फॉल टुवर्ड्स द फ्रंट, एंड दैट goes against the idea of this inertial definition, right? मतलब where did the force come from? किसने तुम्हें धक्का नहीं दिया, फिर भी तुम आगे की तरफ गिर गए, आगे की तरफ तुम्हें फोर्स लगा. Of course there is no force involved, but you experience some change in your state of motion. So clearly ये जो हम discussion कर रहे हैं, that discussion is only valid for very specific frames of reference. It's not valid for all frames of reference. Therefore first law accumulates a lot of information. सबसे पहले it defines what inertia is.
Sir, as you said that in the case of a moving bus, or deceleration takes place or retardation takes place of bus,
Yeah.
so we do not consider as that inertia because of the accelerated frames. But in the books, in like say ninth books, the example is given of the inertia, that it is the inertia that makes us fall forward or backward. Because the feet come in on rest as the bus comes to rest, and the body do not want to come to rest, so it falls forward. So it's kind of inertia.
I understand. So that depends upon your observer. Where is the observer? देखो हम जब स्कूल में होते हैं तो we don't really go into the questions of observers and all, but in college we can. So every motion can be studied from the perspective of an observer. So for example, I was talking about it from the perspective of the observer who experiences the force. But we can also talk about it from the perspective of the observer who is at the ground. So there are two observers. There is this particular observer and this metro experiences some kind of a retardation. And with respect to this observer, he cannot explain where the force came from. Yes.
Yes, sir.
But from the perspective of an observer who is at the ground, for him, the explanation of the forward force that this inner observer experiences is a result of inertia. Yes?
Yes, sir.
So there are two explanations. First of all, the force that this person experiences, according to him, is a pseudo force. But the force that this person experiences, according to this guy, is an inertial force. So it all depends upon the observer. Okay.
Yes.
अगर हम बाहर के ऑब्जर्वर से देख रहे हैं तो वो बंदा जो गाड़ी के अंदर था, it is because of inertia that he moves forward. But अगर हम गाड़ी के अंदर ही हैं, हमें नहीं मालूम गाड़ी मूव कर रही नहीं मूव कर रही है, because there is something known as the equivalence principle. No, not equivalence principle, but something known as that indistinguishability of like अगर आप रेस्ट पे है, अगर यूनिफॉर्म मोशन पे, तो आप नहीं बता सकते. लेट्स सपोज मेट्रो रेस्ट पे है, आपको कैसे मालूम? नहीं मालूम, खिड़कियां बाहर अंधेरा है. लेट्स सपोज बहुत स्मूथली जा रहा है मेट्रो, एक बहुत ही स्पेसिफिक स्पीड पे स्मूथली जा रहा है, तो ऐसा लगता है कि मेट्रो रेस्ट पे है. तो whether or not a frame of reference is at rest or at uniform velocity is a very relative experience. कोई absolute नहीं होता है कि कोई rest पे है या motion पे है. And therefore, every observation is valid. So with respect to this observer, it is an act of inertia. But with respect to this observer, it is an unexplainable act. Would you agree with that? Okay.
Yes.
So with that perspective, I was saying that we can only define inertia with respect to this observer because he is an inertial observer, but we cannot define this property with respect to this guy because he will not agree with it. Because he will say, okay, but I am experiencing a force, iska koi origin nahi hai. So what do you mean by that? So therefore, even though we define inertia as a property that resists, that objects resist change in their state of motion, we must also define at the same time simultaneously inertial frames of reference. We must also define at the same time inertial frames of reference as those frames of reference with respect to which the principle of inertia is valid. So one is incomplete without the other. To define an inertial frame of reference, we need the idea of inertia, what it is, and what it is as a property is also known as a principle of inertia. Okay. But to define the principle in inertia, we require inertial frames of reference, without which we will not be able to maintain consistency. So it's kind of like a circular argument, you know. Inertia is a property such and such, but it's only valid in inertial frames of reference. And inertial frames of reference are those frames of reference in which the principle of inertia is valid. And the principle of inertia is only valid in inertial frames of reference, and inertial frames have only those frames in which the principle of inertia is valid. Can you see that there is a circular sort of a logic going on here? Yeah. Yes.
Yes, sir.
All right. Okay. So yes, there is something called inertial frames of reference. There is something called a property of inertia or a principle of inertia, which is basically the Newton's first law. But there is also the idea that inertial frames of reference exist. Okay, because there are many frames of reference in this universe. There are infinite observers, out of which some of them are inertial frames of reference. So it's a physical statement, not a definition. That inertial frames of reference exist. What do I mean by it? It means that किसी भी system को study करने के लिए we have various reference frames. अगर कोई एक object slide roll कर रहा है इस तरह से down a hill, usually हम इसको study करते हैं with respect to an observer on the ground. But we can also study it with respect to an observer who is traveling in a car. We can also study it with respect to an observer who is traveling in a spaceship. We can also study it with respect to an observer who is on a satellite. We can also study it with respect to an observer who is rolling along with the ball. Are you seeing what I'm talking here? There are infinite observers based on which we can do a study of a mechanical system. Yes or no?
Yes, sir.
Yes, sir.
Yes,
Sir.
but not all of those observers are inertial observers. There are out of the infinite possible observers with respect to whom we can study the system of a ball rolling down a hill. Only a couple of them are going to be inertial or approximately inertial, and only with respect to them the Newton's laws are valid, and only with respect to them we will do the analysis. So the Newton's laws are valid only with respect to the inertial observers. मतलब जहाँ पे law of inertia is valid या the principle of inertia is valid. Okay, and there are inertial observers everywhere. Okay, out of all possible scenarios we will always find an inertial observer. So clearly यहाँ पे this guy is an inertial observer with respect to which whom the law of inertia is valid. This guy is a non-inertial observer with respect to whom the principle of inertia is not valid. In terms of Newtonian mechanics, we are least bothered with the non-inertial observer. We are only bothered with the laws in terms of the inertial observer. और जहाँ पे हम non-inertial frames of reference में जाते हैं, we make certain modifications of pseudo forces, centrifugal forces, Coriolis forces, etc., etc. All right, as you already said, this gives us a qualitative idea of force. So this brings us to what is force. So what is force? Push pull.
That changes the inertial, maybe the inertia of rest or the inertia of motion, that interrupts the inertia of rest or motion.
Like
Force.
as per second, it can be the rate of change of momentum of a body, like change in the velocity or and mass could be also changed by force.
Yes, true. All right. So first of all, the most basic thing is that it is valid only in inertial frames of reference. We don't mention it, but it is implicit because Newton's laws are all valid in inertial frames of reference. Now, what changes the state of rest or state of motion of a body is some sort of a, in very amateur language, push-pull, okay? But a little bit of a more technical language is an interaction, okay? Which will come to in the third law. It's an interaction. Whenever there is some sort of an interaction that one object does with the other, the result of the interaction is that it creates a push-pull. Okay, it creates a certain changed state. All right, हम सुबह सुबह सो रहे होते हैं and we just don't want to get up in the morning. फिर मम्मी आती है आपकी, थोड़ा पानी छिड़क के जाती है and then you get up. Huh? You interacted with her, she interacted with you and created some kind of a disturbance. So the same thing with objects. Objects they don't want to change their state of rest or motion, but there is some other object out there with whom they interact, and it is the result of the interaction that ends up creating some kind of a change in a state of rest or motion. But the second law doesn't talk about the origin of the interaction. The second law only talks about the quantitative idea of what that interaction is. So it gives us a quantitative or operational definition of two things. It gives us a quantitative or operational definition of, first of all, what we call as mass, जिसको हम inertia बोले जा रहे हैं, but inertia का जो quantification है, it is called mass. There are things that you can quantify. You can have an idea. Okay, you can quantify in terms of a scale. So if we can create a scale with which we can quantify how much inertia an object has, we call it as mass. जितना ज़्यादा भारी है उसका मतलब क्या है? दो आइडिया है. There is an inertial mass, there is a gravitational mass. जब हम बोलते हैं भारी है कोई चीज, तो we are essentially talking about gravitational mass. But Newtonian mechanics में we don't really talk about gravitational mass. We are talking about inertial mass. भारी का मतलब है more force is required to create the same kind of an acceleration. So there is a quantitative operational definition of mass plus force. Okay, I have done this discussion in first year, if I remember properly. We take some sort of a thought experiment where there is a frictionless surface, and then we give it some kind of a push, and then based on the push we see that with increasing mass the acceleration decreases. एक ही force अगर हम heavier object पे लगाएंगे तो जितना ज़्यादा heavy object होगा उतना ही उसका acceleration कम होगा, ठीक है. और अगर एक ही ऑब्जेक्ट पे हम ज्यादा से ज्यादा फोर्स लगाते रहेंगे तो एक्सेलरेशन बढ़ता रहेगा. सो देयर इज सम सॉर्ट ऑफ अ रिलेशनशिप कि फोर्स इज डायरेक्टली प्रोपोर्शनल टू एक्सेलरेशन एंड मास इज इनवर्सली प्रोपोर्शनल टू एक्सेलरेशन, एंड दिस इज सम सॉर्ट ऑफ एन एक्सपेरिमेंटल फैक्ट. ओके, इट्स एन एक्सपेरिमेंटल फैक्ट. Experimental fact as well as an operational definition, because it contains the experimental fact that forces are directly proportional to acceleration. Acceleration can be defined based on distances and time periods, and it's an operational definition because we construct this idea of inertia and then we say okay, jitna zyada mass hoga utna kam uska acceleration hoga. So there is an inverse proportionality which is not only an experimental fact but also definite. So based on this we can combine to create this sort of equation that force is directly proportional to time rate of change of momentum. Okay, momentum again is defined as mass times velocity. Okay, this is the most simplistic, or we can say ma. Ma is also a much more simpler one. Now of course यहाँ पे एक implicit assumption ये है that mass does not change during the motion. So Newtonian mechanics, there are many implicit assumptions which becomes clear later on. Mass does not change during motion. Okay, so this is the Newton's second law, and finally, so this gives us an idea about what is the mathematical relationship between acceleration and force and inertia. Okay, and this also starts as the cornerstone. It also starts as the cornerstone of a fundamental equation in mechanics from which all kinds of analysis can begin. So whenever we have any kind of a system we want to study, we start with this equation. We start with this equation and then we can solve it. So this is essentially a second order differential equation. इसको solve करेंगे. So F is equal to, you know, dp upon dt. Okay, or you can write as m d2x upon dt2 for 1D motion. इसको solve करेंगे तो हमें मिलेगा vt. उसको solve करेंगे तो हमें मिलेगा xt. फिर position से हम उसकी trajectory को predict कर सकते हैं. Essentially, this is the construction. When you start with the Newton's second law, and then you solve whatever mathematical necessary tools है उसको use करके, and then you get velocity, position, kinetic energy, momentum, displacement, etc. etc. Okay, there are alternate approaches of work energy theorem, energy, potential energy, वगैरह वगैरह, which are equivalent to this. And we can derive those alternate approaches from this equation itself. Right, so that's the second law. Finally, coming to third law. Anyone? What is the third law?
So pardon for the infusion, but
Yeah.
so force is also something that I believe produces stress, and there is no change in momentum over there. So how do we take that into account using the second law of Newton?
Okay, so usually what happens is that Newtonian mechanics can be applied very successfully to point mass particles, and in certain situations to systems of particles. But whenever we talk about these stresses and all these things, we are usually talking about deformation. Yeah, you're talking about deformation, right? There is some
Right,
kind
sir.
of yeah. So then we don't really talk about Newton's laws, because what really happens, it's not that the Newton's law is not valid, but mostly when we talk about the motion of bodies, we usually talk about rigid bodies. And by definition, rigid bodies are those bodies that do not experience deformation. Whenever deformation happens, the internal energy of the object changes. So whenever internal energy of the object changes, then there are certain things like, for example, mechanical energy conservation is not valid anymore, and various other things also. So Newton's laws are only applied for either point mass particles or systems of particles or rigid bodies. So whenever deformation is happening, we can look at Newtonian mechanics at intermolecular level, but we will not be able to look at the motion of that object that is undergoing deformation. Okay, then that is a difficult process. So that involves a much more complicated thing where we look at how the force is resulting in some sort of a deformation. So there is a subset of study where we talk about elasticity and all these things, but it is not really a concern for mechanics, because वहाँ पे motion of the object नहीं हो रहा है, वहाँ पे deformation of the object हो रहा है. So Newtonian mechanics is more restricted to the motion of the object, the displacement in terms of its position in space, na ki its deformation as its shape is concerned. Okay, am I making sense? So in a way, Newtonian
Yes,
mechanics
sir.
is limited to just analyzing the mechanics of it. But जहाँ पे deformation की बात आती है, थोड़ा सा वहाँ पे हाँ, we go into a different sort of a field that Newtonian mechanics is usually not concerned with. Then use कर सकते हैं हम in certain situations, but mostly it comes in the field of all these things, elasticity, plasticity, stress, strain, and different kinds of modulus and all those things. Okay.
Right, sir. Thank you.
Because the force that you provide is kind of absorbed in the intermolecular bonds that create, or the breaking of the bonds that construct that body in the first place, not in displacing them, but in in breaking of the bonds, or deforming the bonds, or sliding layers of molecules on top of each other.
But sir, the fundamental nature of the force, does it remain the same or does it vary in such cases?
No, what is a force? It's an interaction, right? So we're talking about 2 point masses that are interacting with each other, and because of the interaction, what happens to their changes in their position. Now, a rigid body is a very complicated body containing a large number of atoms and molecules, and every single atom is also interacting with each other. So there is a change in their relative positions. ऐसा नहीं है कि deformation होता है तो वहाँ पे कुछ changes नहीं हो रहे. The atoms are also getting displaced, and they are maybe creating new layers and new bonds, and so all this deformation is taking place, and ultimately that is coming from some external interaction. Yeah, so it is there, but as a whole the object has not moved, but that force has resulted in the displacements of these individual atoms and molecules and these layers of crystal structures. Okay.
Yes, sir. Thank you.
Okay, now coming back to third law. What do you think is the third law? What does it tell us apart from action and reaction? Anyone? Apart from action reaction, what information is contained in the third law?
So that the forces applied are equal in magnitude and opposite in direction.
If there are
Same
two
thing that is
bodies, that are interacting with each other, they both experience forces due to each other, and these forces are equal in magnitude and opposite direction. Yes, very good. That's for every action there's an equal and opposite reaction. Anything else? Anything new? You're third year students. Come on. Any further information contained in the third law?
Forces are created in pairs.
Forces are created in pairs. Very good. Yes. So in a way, the third law tries to explain the origin of forces. Okay. First law tells us what happens in the absence of forces. Second law tells us what happens in the presence of forces. The third law goes into the why do forces exist in the first place. It tells us that Forces can only exist when there is an interaction. Like for example, friendship, दोस्ती. दोस्ती कहाँ होती है? When there are minimum 2 people. है ना? I know आजकल लोग बोलते हैं अपने आप से दोस्ती कर लो, but usually अकेला इंसान में दोस्ती नहीं होता ना. Are you understanding what I'm saying? So forces can only exist in pairs. मतलब when there are 2 objects. If there is one object in the entire universe, it will never experience any force. अगर पूरे universe में सिर्फ एक particle है, let's suppose that in the entire universe there's just one particle, there is no concept of a force. There is no such thing as a force. Force exists because there are other particles around. So force in itself is an interaction. It's a relationship between 2 particles. Are you following?
Yes.
So it explains the origin of forces. And it says that forces always arise, only arise in pairs. इसका मतलब ये है कि अगर ये हमारी धरती है और ये पेड़ है, सॉरी पेड़ इंसान बना दिया, ये पेड़ है और एक एप्पल है जो गिरता है धरती में, तो इन अ वे द अर्थ आल्सो एप्पल की तरफ गिर रहा है. वो दिखता नहीं है बिकॉज उसका मास बहुत ज्यादा है और मास इज इनवर्सली प्रोपोर्शनल टू एक्सेलरेशन. अगर एक एप्पल एक सेब पेड़ से अर्थ की तरफ गिरती है तो अर्थ भी सेब की तरफ गिरता है एक तरीके से. देयर इज अ म्यूचुअल फोर्स बिटवीन बोथ ऑफ देम. So it's not that the apple is falling towards the earth, but the earth is also falling towards the apple. It's just that we don't see it. It's very negligible. And it's true for everything. The earth is not going around the sun. The sun is also going around the earth, but the more precise statement will be there is a center of mass between the earth and the sun the sun is going around that center of mass and the earth is going around that center of mass. Same thing with the moon. You know, the moon is not really going, हमें ऐसा लगता है because there's a very huge difference in the mass. Earth is very massive, so हमें लगता है the moon is going around the earth. ऐसा नहीं है. Both are going around each other with respect to a common center of mass. All right. So everything that exists in the world, every kind of a force that exists, everything originates in terms of pairs. And if there is an object that experiences a force, all right, then with respect to that force, there will be another object that also experiences a similar kind of a force, such that these 2 forces are exactly equal in magnitude and opposite in direction. So F12 is equal to F21. Okay, these forces always act in different particles, in different bodies, and in different directions. So in a way, the Newton's 3 laws are complete because the first law talks about what happens in the absence of forces. The second law talks about what happens in the presence of forces. It gives us a quantitative definition. It gives us an expression, a differential equation from which to start our analysis. And the third law kind of completes the whole story by telling us why forces exist in the first place. Otherwise, it will not be complete in that sense. ठीक है? Any questions?
None, sir.
Okay, so these are the Newton's laws. We can talk a lot about the Newton's laws, but again, you guys know the story anyways. So let us look at what sort of an analysis is possible. All right, the Newton's laws ko lekar ke. So we keep many of these things in mind, but we don't really say it. The fact that we are dealing with inertial observers, the fact that we are making observations based on inertial frames of reference, the fact that forces only exist as interactions. हम बहुत सारी चीज़ों को neglect कर देते हैं when it comes to problem solving, and we only put emphasis on the second law. And then, as long as those things are correct and valid, we'll get the right analysis. But sometimes if they are not valid, then we may not necessarily get the right analysis. So we just keep that in mind. Okay, but how do we actually approach a problem? So there are two kinds of systems. First is a point mass particle in which we will do some sort of an analysis, and second is the systems of particles in which we can do some analysis. So first, let us start with mechanics of point mass particle. Mechanics of a point mass particle is quite simple. You know, first of all, you have some sort of a frame of reference, okay? Because all kinds of measurements that we do is with respect to some coordinate system. Because if you want to measure velocity, if you want to measure acceleration, if you want to measure momentum, you will need to measure distances and time periods. So distances can only be measured with respect to some kind of a coordinate system where there is an origin, and with respect to that we can measure distances. Time is not given that special importance in Newtonian mechanics. We just think that we have a clock or a watch, and based on some t is equal to 0 randomly defined, we can measure time. So we have some kind of a coordinate system, and the most common coordinate system is the Cartesian coordinate system, the rectangular Cartesian coordinate system, where there is x, y, and z axes perpendicular to each other, and the components along those axes gives us 3 different distances, and we can construct a position vector of any kind of a particle that is experiencing some kind of a motion. So let's suppose there's a particle experiencing some sort of a motion, then the instantaneous position of the particle is given by what is known as the position vector. Okay, so position vector R, and usually if the particle is in motion, then R is going to be a function of time, because at some time it's going to be somewhere else, at the time before it was somewhere else, because it is experiencing some motion. So this is the position vector, which is usually the most a desired physical quantity of interest, because once you do have the position vector, from here you can derive everything else. So if you have R, okay, you know the trajectory, then done. That's all we want, because from here you can come up with what is dr upon dt. You can come up with what is velocity. From here you can come up with what is the acceleration experienced by that body. You can come up with what is momentum. You can come up with what is kinetic energy. You can come up with various other things. You can come up with what is the potential energy expression associated with this. Any kind of a physical quantity that you want, we usually are interested in this. Okay, but ये हमें नहीं मालूम होता है, ये हमें पता करना पड़ता है. Okay, we start with the second law and then ये हमें पता करना पड़ता है. Okay, so essentially we can define, if we know the position vector, we can define the velocity as the first order derivative of the position vector. We can define the acceleration as the second order derivative of the position vector. We can define momentum also, linear momentum बोलते हैं. All right, now if this particle is experiencing some kind of a interaction, ऐसा जरूरी नहीं कि interaction is only one, it can be multiple interactions. If there are multiple interactions, then what we do is we follow what is known as the law of superposition. Okay, so forces follow the law of superposition. You know what that means? No, vector sum. Okay, if there are multiple forces acting on a body, then we can say that the net force acting on the body is essentially a vector sum of all the forces. Okay, it's a vector sum of all the forces. Okay, if there are multiple forces acting on a body, so if you have an object, there is a force acting in this direction, acting in this direction, acting in this direction. So इसका जो effective force है, that is all we need. Okay, we need its effective force or the net force. We don't need to do the analysis with respect to each individual force. We only need to do the analysis with respect to the net force or the effective force only. Okay, so अगर हमारे पास एक position vector है R, all right, and हमारे पास some sort of a net force है, in that case it automatically follows from the second law. So this is where the second law comes in, that the F net is responsible for its motion in such a way that you can write it in this manner. Okay, और इसको लिख सकते हैं d by dt of mv, and if this is equal to m dv upon dt or is equal to ma, under the assumption that we are dealing with mass does not change during motion or non-relativistic scenarios. non-relativistic cases that dm upon dt is equal to 0. All right. So this is essentially the starting point. Okay, this is essentially the starting point, and any kind of an analysis is a solution of this differential equation. Solution of this ODE. Okay, majority of Newtonian mechanics में अगर आप लोगों ने देखा होगा या whatever kind of problem has come in the examination is focused on trying to solve this differential equation by various methods. You know, sometimes we do a direct tackling, sometimes we don't do it direct tackling, we do indirect methods. Okay, now in the indirect methods comes following some sort of a conservation law, yeah, some kind of a principle that is equivalent to the Newton's laws, but we give it a specific name because of their importance. Okay, so this brings me to various kinds of conservation theorems. Are you following the discussion, guys?
Yes, sir, we are here.
Yes, sir.
Yes, sir.
All right. All right. So one approach is, and we can spend a lot of time in this, how to, कोई भी problem आता है, you start with the Newton's second law and then you approach it. This can take 30 hours of classes. You know, there are so many problems out there, so many problems. Kleppner में ही कितने सारे हैं, and if you are preparing for some kind of a competitive exam, you know how many problems are there. But physically speaking, as far as the concept is speaking, this is the concept. That's it. You have a Newton's second law, you try to solve the differential equation, and then you do whatever mathematical tricks necessary to come up with your answer. Okay. There are some equivalent theorems, conservation theorem जिसको हम बोलते हैं, which is kind of equivalent to the Newton's laws, but we give it a specific name because there is some sort of a conservation that is happening. But so coming to this question, what do you mean by conservation? Conservation का मतलब क्या है? Conservation of trees, plants, wild animals, species. What do you mean by conservation in terms of physics? What do you understand by the word conservation?
To save.
To save. Okay. Okay. In terms of physics, what does it mean?
To make a theorem valid.
To make a theorem valid. The validity is not related to conservation. What do you understand by conservation theorem? Conservation theorem में conservation का meaning क्या है? Conservation का what is in physics the
सर खत्म नहीं होना.
खत्म नहीं होना. Okay.
Remains constant throughout motion.
Remains constant. Okay. थोड़ा सा we are near the answer. Not always. Anything else? Anything else? What do we mean when we say conserved quantity? Conserved quantity.
Sir, same रहना. Sir, वैसे
same रहना. Same रहना. Okay, what do you mean by invariant quantity? Anyone?
Which does not change with respect to change in coordinate system.
Very good. Very good. Invariant quantity is something that does not change with respect to a change in the frame of reference or coordinate systems. So is the conserved quantity meaning and invariant meaning same, or is it different? How is it different?
Sir, conserved quantity is the value of the invariance is something to do with coordinates, right?
Invariance has to do with transformation of coordinate transformation. So conserved quantity has to do with what? It doesn't have to do with coordinates, right? It is not associated with transformation of coordinates. So how is it different? If I say something is conserved, what do I actually mean? It remains constant. Okay, anything more? It's a right answer. It's not an incorrect answer. Anything more? Because invariant may be though it is constant. So what do you actually mean by it remains constant? No one?
Like before and after the interaction, that particular property or quantity of an object does not change. Like
Very
if we
good.
see the whole system.
Yes, yes. Before and after a process has happened, before and after an interaction, during the evolution of a system, anything. All right, we're not talking about going from one frame of reference to another. We are talking about the process or the evolution of a system. If a particle is moving from here to here, we are talking about the evolution of that system. If there are two particles that are interacting, what happens after the interaction? Okay, so we are really talking about over a period of time, the evolution of a system. Okay, we are really talking about what happens to a particular quantity as a system evolves. As a system evolves, as a system undergoes transformation, as particles go from here to there, as particles collide, as particles rotate, or whatever it is, all those things happen, but something remains the same. A physical quantity remains same. It remains constant. And then in that situation, we say that that quantity is a conserved quantity. Okay, and in physics, conserved quantities are very important. We give a lot of respect and a lot of importance to conserved quantities. Why? Well, because they can help us like an anchor even to figure it out how the system is evolving. अगर एक quantity, अगर एक system था, एक particular state में था, एक quantity का value एक है, और वो system change हो गया, but वो quantity same ही है, तो we can figure out how the change has happened. It's a very important quantity because it hasn't changed. It remains the same. So it behaves like an anchor, you know. So in physics, there are a couple of quantities which are conserved. Whenever a system evolves, it doesn't change. The value of the quantity remains the same. So which is the most common basic conserved quantity?
Mass.
No, mass is an invariant quantity. Mass is not a conserved quantity.
Energy.
Energy, yes. Energy. Energy is पहले
Momentum.
linear momentum. Yeah. So we talk about the conservation theorem. Of linear momentum. Okay, so what is the conservation of a linear momentum tells us? It tells us simply the first law itself. First law का ही एक restatement है that if the total force acting on a particle is zero, then the linear momentum is conserved. That's it. If the total force acting on a particle or a system of particles if the total force acting on a particle or a system of particles is zero, then the linear momentum is conserved. Okay, we can simply prove it from our Newton's second law. Okay, that if F is equal to 0 implies dP upon dt is equal to 0 or P is equal to a constant. If it's a system of particles, there's a multiple particles. If the net force is equal to 0 and there are a large number of particles, d upon P I, then if F is equal to 0, then this is equal to d upon summation of Pi. So this is summation of Pi is equal to constant. Okay, it means that कोई भी अगर एक सिस्टम है इवॉल्व कर रही है बट एक्सटर्नल फोर्स नहीं लग रहा है तो उनका जो लीनियर मोमेंटम है पूरे सिस्टम का कांस्टेंट रहेगा. So for example, if you have a box of particles and they are interacting with each other, okay, but they are not experiencing any external force, then the linear momentum of the entire system will remain constant. और सिस्टम जैसे भी इवॉल्व करे, we can in fact predict, and this leads to collision questions. You know, दो पार्टिकल collide कर रहे हैं but there is no external force, then what's going to happen? All right, the center of mass remains constant, or the center of mass goes at constant velocity. For example, दिवाली में पटाखे तो फोड़े होंगे कभी, है ना?
Yes, sir.
अगर तुम कोई पटाखा फेंकते हो ऊपर और ऊपर पटाखा फट जाता है दो हिस्सों में, है ना? दो हिस्सों में फट जाता है, एक हिस्सा यहाँ चला जाएगा और दूसरा हिस्सा यहाँ चला जाएगा. ओके, तो based on conservation of linear momentum, what can we say? We can say that इसका जो center of mass है, it will come to its original place. ना फटता तो जहाँ गिरता, सेंटर ऑफ मास वहीं पे होगा. तो वी कैन प्रेडिक्ट, अगर मेरे को मालूम है कि ये पीस कहाँ गिरा तो मैं ये भी प्रेडिक्ट कर सकता हूँ ये पीस कहाँ गिरा, है कि नहीं?
यस सर.
इस तरह के क्वेश्चंस भी तो किए होंगे ना, कि मतलब मेरे को अगर मालूम है कि एक पीस कहाँ गिरा, इसका मास कितना है, ये डिस्टेंस कितना है, तो मैं प्रेडिक्ट कर सकता हूँ कि दूसरा पीस कहाँ गिरा, इसका मास कितना है, कितने डिस्टेंस पे गिरा है. व्हाई? बिकॉज द ओरिजिनल ट्रैजेक्टरी रिमेन्स द सेम. सो इवन इफ देयर आर, एक पार्टिकल दो हिस्सों में बढ़ जाता है, द नेट सॉर्ट ऑफ अ ट्रैजेक्टरी रिमेन्स द सेम. यहाँ पे हम ऑफ कोर्स एक्स एक्सिस में फोर्स की बात कर रहे हैं, क्योंकि वाई एक्सिस में तो ग्रेविटी है, तो of course we are not talking about that, but in the x-axis, right? So essentially this is the conservation of linear momentum that we can apply in various kinds of problems related to collisions, which simply says that if there is no force, external force acting on the system, it means that तुम्हारा जो है system will evolve in such a manner that the total linear momentum of that system will remain a constant throughout its motion. Okay, all right, what is the next important conservation rule? Another important conservation rule. Energy is there, yes, yes. I'll come to energy. Any other?
Angular momentum.
Angular momentum, very good, yes. So whenever we talk about point mass particles, we not only talk about linear motion. Linear motion means an object traveling along a line or a curve, okay, but we also talk about rotational motion. रोटेशन का मतलब है an object moving with reference to an origin या and a rigid body rotating about a particular axis. So Newtonian mechanics, we can divide it into, you know, the traditional translational or linear sort of a motion, and the what you study a little bit later, the rotational or rigid body dynamics. And when it comes to rigid body dynamics or rotational motion, we have what is known as a conservation of angular momentum. What does the conservation of angular momentum tell us? क्या बोलती है? What does it say?
If torque about the point is 0, then angular momentum remains constant about that point.
Yes, very good. If the torque experienced by a particle about a particular point is 0, then the angular momentum experienced or angular momentum of that particle or a system of particles about that point will remain constant. Okay, so quite simply put, we can define these quantities also. So for example, जो linear momentum का rotational analog है, of linear momentum, it is known as angular momentum, which is R cross P. Okay, and the rotational analog of torque of force, it is called torque, which is R cross F. Okay, now if we look at the Newton's second law, if we look at the Newton's second law, then F is equal to dp upon dt. Okay, now if we say R cross F is equal to R cross dp upon dt, then this can be written as, or R cross F is equal to d upon dt of R cross P. Okay, so how can I prove that these two equations are exactly the same? So let us check. So d by dt of R cross P is equal to R cross dP upon dt plus dr upon dt cross P. So this is equal to R cross dP upon dt plus dr by dt क्या है? V है, and P क्या है? mv है. So cross product of velocity with velocity is going to be how much?
0.
Zero.
So this is going to be 0. So therefore you end up getting R cross P, R cross dP upon dt. So R cross dP upon dt. So therefore, based on our definitions, this becomes the left hand side the torque, and this becomes angular momentum. So we end up getting the rotational analog of the Newton's second law. Okay, so this is the rotational analog of the Newton's second law. Newton's second law in translational motion. Okay, so this gives us a similar kind of a framework for analyzing rotational motion. So if you're looking at particles motion around a given point or an axis, or a rigid body's rotation about some axis or some kind of origin of a coordinate system, then we can rely upon this law as much as we can rely upon the Newton's second law. All right. So based on this, we can come up with a similar kind of a conservation law, that if the torque experienced by a body, so if torque is equal to 0, then quite simply put, dl upon dt is equal to 0, or L is equal to a constant. Okay, the angular momentum is a constant. So if the torque experienced by a system of particles is 0, then the angular momentum of that system is preserved. Then the angular momentum of that system is conserved. Anybody can give me an example of a conservation of angular momentum principle?
सर व्हील वाली चेयर पे जो बैठते हैं, जो मतलब जो व्हील वाली चेयर होती है ना, जो घूमती है ऐसे,
व्हील चेयर,
नॉट व्हील चेयर, नॉर्मल डेस्कटॉप चेयर. या
हाँ, उसमें क्या करते हैं?
हाँ, वो उसको चेयर को ऐसे घुमाओ जो पहियों के साथ. हाँ, सो जब आर्म्स वाइड अपार्ट कर लेंगे तो वो स्लो हो जाएगी, और फास्ट नहीं स्लो हो जाएगा, और जब पास जाएंगे तो
आर्म्स वाइड अपार्ट तो क्या हो जाएगा फिर? रोटेशन स्लो, और आर्म्स को क्लोज कर देंगे तो
फास्ट.
I1 ओमेगा 1 इज इक्वल टू I2 ओमेगा 2. सो एक का मोमेंट ऑफ इनर्शिया कम हो गया तो एंगुलर फ्रीक्वेंसी बढ़ गई, है ना. मोमेंट ऑफ इनर्शिया ज्यादा हो गया तो एंगुलर फ्रीक्वेंसी घट गया. ऑलराइट, दैट्स ट्रू. एनी अदर एग्जांपल?
और मतलब इसी के साथ हाथ में अगर हम व्हील भी पकड़ ले तो भी होता है.
हाथ में
व्हील पकड़ ले, रोटेटिंग व्हील,
रोटेट
और
करता
उसको
हुआ.
अगर रोटेट करेंगे हम लाइक हॉरिजॉन्टली रखेंगे तो इट वुड add to the momentum. या मतलब
It's actually like if you keep it horizontal, you will turn about at the same rate. But if you rotate it if you keep it vertically, you will rotate about at the same rate. But if you keep it horizontally, it will provide you with the momentum. For example, the chair has very minimum friction to offer. So if you're sitting in the chair and there's a wheel rotating in a particular direction, say clockwise direction, then it will push you in the opposite direction to it. Are you able to visualize what I'm trying to say?
You're talking about the precision of a gyroscope, right?
Right.
You're talking about the precision of a gyroscope. All right. Yeah, I understand. So, so can you give me a simpler example? Precision of a gyroscope is a little bit complicated. क्या है?
बैले डांस.
प्लेनेटरी मोशन.
किसका मोशन? नेट. Planets का मोशन. Planets का मोशन में, yeah, it's restricted to a plane. Yeah, Conservation of angular momentum means the direction of angular momentum remains constant, because the torque experienced due to gravitational forces is zero, and because torque experienced due to gravitational forces is zero, the angular momentum of a planet revolving around the sun is constant. And one significance is that its direction, because angular momentum is a vector quantity, direction always remains the same. Therefore, we are always on the same plane. So sun अगर ऐसा है तो अर्थ ऐसे नहीं जा रही है, अर्थ ऐसे नहीं जा रही है, बल्कि अर्थ एक प्लेन में जा रहा है all the time in one constant plane. That's a very good example. Good. In fact, you can see that majority of the planets in a solar system are on the same plane, kind of in the same plane. Any other example? Simple example. Hoverman बोलते हैं, Hoverman क्या बोलते हैं, Hubleron क्या बोलते हैं उसको, Hoverman sphere बोलते हैं ना. It's like a kind of a Lego kind of a चीज जो ऐसा एक sphere बनाते हैं, and the moment you pull a wire, it becomes big, and then it's rotating and it becomes small. So when it becomes big, so it starts going at lesser angular velocity and becomes small, it goes at greater angular velocity. Any other example? No? That's all? Any other example is there?
सर मौत का कुआं जो होता है ना,
मौत का कुआं, कंजर्वेशन ऑफ एंगुलर मोमेंटम कैसे हो गया वो?
तो बैंकिंग हो गई।
तो जो नेट, हाँ,
कंजर्वेशन ऑफ एंगुलर मोमेंटम नहीं हुआ, दैट्स अ लिटिल बिट कॉम्प्लिकेटेड. अच्छा एक बात बताओ, साइकिल चलानी आती है?
यस सर.
यस सर.
यस सर।
जब साइकिल चलाते हो बैलेंस होते हो, खड़े खड़े बैलेंस कर सकते हो?
नो सर.
क्यों नहीं कर सकते?
जायरोस्कोप नहीं है सर।
और चलाने के टाइम पे बैलेंस कैसे हो जाता है इतना आसानी से?
अरे सर एक वीडियो देखी थी, मैंने भूल गया. मतलब इट इज डिजाइन इन सच अ वे कि जब हैंडल इस तरफ जाता है तो बॉडी इस तरफ जाती है, तो उसको स्ट्रेट मतलब स्ट्रेट रखने के लिए
डायरेक्शन मोड़ने की बात ही छोड़ो,
एंगल मोमेंटम की डायरेक्शन को वो रखने के लिए.
डायरेक्शन की बात ही छोड़ो, तुम सीधा जाओगे तो बैलेंस होता है ना. 1 घंटे तक चला सकते हो सीधा, बैलेंस है. लेकिन क्या तुम 1 घंटे तक खड़े खड़े बैलेंस कर सकते हो उसको? What is the reason? What is the answer to that question?
सर चलाते टाइम सर हम वो उसके सेंटर ऑफ मास पे फोर्स लगा रहे होते हैं बाइसाइकिल के और अपने सिस्टम पे.
हाँ, फिर क्या उससे बैलेंसिंग का क्या है मतलब?
सर सेंटर ऑफ मास पे फोर्स टॉर्क प्रोड्यूस नहीं करता एक्स्ट्रा.
Not the correct answer. It has to do with conservation of angular momentum. Anyone can explain what happens when you ride a bike that you can balance it easily, but a bike at rest you cannot balance. It's very difficult to balance. It goes back to the Pratham's example of a gyroscope. Now there is a wheel, right? And that wheel is rotating. Yes, ये पहिया है, rotate कर रही है. कर रही है कि नहीं?
Yes sir. Yes sir.
So this axis, okay, there is a certain amount of force that is required to change the plane of the direction of this axis. ये व्हील रोटेट कर रही है ना. अगर तुम हाथ में व्हील पकड़े हुए हो, सोचो कि तुम पैरों के साथ व्हील पकड़े हुए हो, तो when the wheel is in motion, it has a particular angular momentum associated with it. And whenever there is an angular momentum associated with it, under ideal circumstances, this wheel doesn't want to tilt, because tilting would require an external force. But when it is not rotating, tilting is very easy. Just a little bit of imbalance in the forces is easy. It creates a tilt. But when it is rotating, tilting requires an external force. कभी वो घुमाया है हाथ में, पहले आता था ना, यार घुमाते थे, क्या बोलते हैं उसको, एंजाइटी डिवाइस, फिजिट स्पिनर घुमाया है.
Yes sir.
फिजिट स्पिनर घुमाते हो तो उसका प्लेन चेंज करने में फोर्स लगता है ना. कभी एक्सपीरियंस किया है? घुमा करके उसका प्लेन चेंज करने की कोशिश करो,
वो स्लो डाउन भी हो जाता है फिर.
अगर फिजिट स्पिनर घुमाते हो बहुत फास्ट और उसका प्लेन को चेंज करने की कोशिश करते हो ना, तो वो बहुत फोर्स लगता है, इट रेजिस्ट्स. सो व्हेनेवर देयर इज अ व्हील और अ सर्कल रोटेटिंग, उसके प्लेन वो इट डजंट वांट, इट रेजिस्ट चेंज इन इट्स डायरेक्शन ऑफ इट्स प्लेन. उसका प्लेन गोज बैक टू दिस आइडिया. It doesn't want to change its plane. So the cycle का wheel also doesn't want to change its plane. ठीक है, जिस प्लेन में रोटेट कर रहा है उसी प्लेन में रहना चाहता है. It resists change in the plane. Therefore, it is easy to balance. Now can you visualize?
Yes, sir, absolutely.
Yes, sir.
So that goes back to conservation of angular momentum. All right. So these are clearly very important conservation theorems. Let's go to the next, which is conservation of energy principle. You have conservation of linear momentum, conservation of angular momentum. Thirdly, conservation of mechanical energy, and not just conservation of mechanical energy, with it is associated with an alternate approach to Newton's second law, which is the work energy theorem. All right. So what does the work energy theorem tells us? It simply gives us an alternate approach to analyzing a problem without actually having to solve the differential equation, that is a Newton's second law. So for example, if an object goes from point 1 to point 2, we can say that the work that is done for the object to go from 1 to 2 is equal to the line integral of the force that is involved, that is responsible for creating that displacement, and dr as it goes from 1 to 2 along that particular path. Okay, this is known as the work energy theorem. In fact, this is equal to the change in the kinetic energy. और मैं derive करता हूँ उस चीज को. Let me derive it. Okay, so what is force? F is equal to m dv upon dt. Okay, so यहाँ पे अगर हम इसको लिखेंगे, it goes from 1 to 2 along a certain kind of a path. So we have m dv upon dt dot dr. What is d? What is v? V is equal to dr upon dt, or we can say that dr is equal to v dt. Okay, so this can be written as 1 to 2 m dv upon dt dot v. Okay, इसको हम कैसे लिख सकते हैं? We can say that d upon dt of v dot v is equal to v dv upon dt plus v dv upon dt is equal to twice v dot dv upon dt. Therefore, this can be written as v dv dt can be written as half m d by dt of v dot v. Okay, so it's a dot product. So 1 to 2 dot product का मतलब है square लिख सकते हैं direct, d by dt of v square we can just write similarly. Okay, नहीं यहाँ पे एक और चीज था ना, v dt था यहाँ पे, सॉरी, v dt 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 of v square dt. So therefore this can be written as half m dv square. So this is equal to half m v square between 1 to 2, 1 to 2, 1 to 2. Therefore, finally we have the work done in displacing a particle from one point to another under the experience of some kind of a force can be written as the difference between the quantity half mv2 square minus half mv1 square. ठीक है, calculation is clear?
Yes, sir.
Now, of course, this is very, very important. We have created a new definition of what work is. So it defines what work is. But now we see these quantities arising all the time and we need to define them. Okay. So as it turns out, this is a quantity that very much depends upon velocity, and we define it as kinetic energy. Okay. We define it as kinetic energy. So whenever some object is experiencing some sort of a motion, let's suppose an object slides down a hill and I know its velocity here and I know its velocity here, then I can calculate the amount of work done between 1 and 2 if I know their velocities. And from there, I can know about other things like what is force and etc. all these things. Okay. Now, as it turns out, there are two kinds of scenarios where we can do some further analysis. Further analysis is possible whenever we look at this particular quantity known as work done. Okay, so let's look at the work done. Now, as it turns out, this line integral, this is a line integral, right? It's a line integral of force with respect to the displacement. In some situations, this line integral depends on the path. So the particle that goes from here to here, from 1 to 2, it depends on the path. Like if it follows this path C1, it may have a different value. If it follows this path C2, it may have a different value. If it follows this path C3, it may have a different value. So in certain situations, this work done as an object goes from 1 to 2 following different paths will have different values. But in certain situations, doesn't matter which path they follow, it has the same value as long as the endpoints are the same. So this leads to two different scenarios, and it ultimately boils down to the nature of the force involved. So this leads to the two situations of two kinds of forces involved. What are those two forces, guys?
Conservative and non-conservative.
Very good. So we have what is known as conservative forces, and what we have non-conservative forces. So essentially, conservative forces are those forces in which the line integral of f dot dr as it goes from 1 to 2 is independent of path, okay. Non-conservative forces are those as it goes from 1 to 2, f dot dr is dependent on the path. Now, if you have studied vector analysis and all these things, you will know that there are certain consequences to this very simple idea that a line integral of some kind of a vector quantity is independent of the path or not. So as you can show that if the line integral of f is independent of path, in that situation, the curl of f is going to be how much?
0.
0. In the other situation, if the line integral of f is dependent on the path, the curl of f is not equal to 0. There is another consequence that if the curl of some kind of a vector field is equal to 0, then that kind of a vector field can be written as a
Negative
gradient of some kind of a scalar potential function, which I am going to refer to as potential energy. All right, this is not possible in the second case scenario. So whenever there is some kind of a force that behaves in such a manner that the line integral or the work done is independent of the path, in that kind of a situation, that force can be written in terms of a negative gradient of some kind of a scalar potential or a potential energy function. So can you give me a couple of examples of conservative forces?
Gravitational force.
Gravitational force, okay.
Electrostatic force, spring force. Electrostatic force.
Electrostatic force, very good. And
spring force.
Spring force. In fact, any kind of a central force or a constant force, they are all conservative forces. Okay. Non-conservative forces, any example?
So friction, tension. Normal force.
Tension. And can you tell me some kind of a natural interaction which is non-conservative?
Viscous.
Yeah, dissipative forces, any kind of a dissipative force. Dissipative forces and nothing. Guesses? Non-conservative forces.
Magnetostatic force.
Magnetic force is non-conservative? Yes or no? Is magnetic force conservative or not?
It's not dependent upon the path, so should be conservative.
What is the work done if a charged particle revolves in a circle around a magnetic field? 0?
Sir, line integral, closed line integral तो sir mu naught I n close आता है.
हाँ तो 0 होता है ना अगर हम सिर्फ उसको इग्नोर करें. If we look at just the work done, if an object goes and travels around a closed path.
But sir, for magnetic fields, we define vector potential, not scalar potential.
Okay, so is it conservative or non-conservative?
So sir, non-conservative.
Yeah, it's not conservative. Anyways, it doesn't come under the category of conservative, non-conservative. Any other force, natural force, that is non-conservative. What about nuclear forces? Are they conservative? No idea. All right, so let us proceed further. So if, as I said, if the line integral of the force is independent of the path, then we can write the force in terms of a negative gradient of a scalar potential function, which is the potential energy. In that kind of a situation, if I define the work done as it goes from 1 to 2, so this is F dot dr as it goes from 1 to 2, in that scenario, I can write F as a negative del v dr 1 to 2 is equal to, so यहाँ पे हम क्या लिख सकते हैं, I can write the total differential of v as del v upon del x dx plus del v upon del y dy plus del v upon del z dz. So this can be written as del v upon del x I cap plus del v upon del y j cap plus del v upon del z k cap dot product of dx I cap plus dy j cap plus dz k cap. लिख सकते हैं ऐसा? लिख सकते हैं ना?
Yes, sir.
Yes,
So
sir.
what is this? This is nothing but the del operator v dot dr. Yes. तो यहाँ पे आ जाएगा हमारा dv from 1 to 2. So this is equal to minus v2 plus v1. So the work energy theorem therefore now takes a new form, minus v2 plus v1. Okay, so this is the work energy theorem for conservative forces. So we had this work energy theorem for we had this is equal to ke2 minus ke1 for in general cases, but for conservative forces where the line integral of the force is independent of the path, we can write the work energy theorem, restate that as the negative difference of the potential energy. So in a sense, while kinetic energy depends upon the velocity, potential energy is something that is purely based on its position. Okay, potential energy function is something that is purely based on the position. So based on a position, we can denote some sort of an energy to an object. So for example, agar hum potential energy calculate karte hain, I say that if you take an object from height h1 to h2, the potential energy is equal to mg h2 minus h1. Okay, so it purely depends on its position. All right, and then the reference is just purely based on my choice. So we'll be talking about potential energy function a lot because Lagrangian contains the potential energy function and the kinetic energy function. So we'll be talking about that later. But one consequence that I'm trying to arrive is if we combine both, so W21 is equal to KE2 minus KE1 is equal to minus V2 plus V1. If we combine both, so this becomes KE1 plus V1 is equal to KE2 plus V2. So we say that because this is something that is dependent upon the position 1 and its velocity at that point. This is something that is dependent upon its position and some sort of a function of that position. And this is dependent upon position 2 in its velocity. And this is some sort of function based on its position at 2. So they are completely different. They're sort of independent of each other. That is only possible if this whole configuration, if the whole expression is some kind of a constant. And we say that this constant is nothing but the energy, okay, mechanical energy. So we say that the mechanical energy E1 is equal to KE1. So we say that the mechanical energy at position E1 is equal to the mechanical energy at the position 2. So this leads to what is known as the conservation of mechanical energy principle. Okay, so mechanical energy, it's mechanical means it's different from thermal energy, light energy, etc., etc. So mechanical energy, we are only restricted to the discussion of potential energy as in some kind of an energy function based on its position, and kinetic energy as in some kind of a energy based on its velocity. So this is another sort of a very important conservation law in physics, that if forces acting on a particle are conservative, if forces acting on a particle are conservative, if forces acting on a particle are conservative, then the total mechanical energy, of the system remains conserved. Clear है यहाँ तक?
Yes, sir. Yes, sir.
Alright, so जब हमने न्यूटन मैकेनिक्स डिस्कस किया था पॉइंट मास से रिलेटेड, हमने या तो सेकेंड लॉ का सॉल्यूशन डिस्कस किया होगा, या तो कंजर्वेशन ऑफ लीनियर मोमेंटम, कॉलिजन्स, ये सब डिस्कस किया होगा हमने, या तो कंजर्वेशन ऑफ एंगुलर मोमेंटम रोटेशन के टाइम पे डिस्कस किया है, कंजर्वेशन ऑफ एनर्जी डिस्कस किया है, वर्क एनर्जी थ्योरम डिस्कस किया, यही तो है बस. एंड फर्दर यूजिंग दीज थिंग्स इन वेरियस सिनेरियोस, दैट्स ऑल वी हैव डन. Now there is a little bit of an extrapolation from here, which is the mechanics of systems of particles. Okay, it's not enough to just say that these laws are valid for a point mass particle, so it's valid for everything else. I also need to mention, at least आज ही खत्म कर दूंगा. Okay, I'll not carry forward this discussion to the next class, but it's important to mention that the similar kinds of rules also hold true for systems of particles. So let us talk about the mechanics of systems of particles. Okay, so till now we were only discussing about a point mass particle. Point mass particle का मतलब क्या होता है? It's a theoretical particle that occupies no volume, no shape, no size, and occupies a fixed position in space. Okay, infinitesimally small, maybe massive. Can anybody give an example of a point mass particle? A real particle that we can assume to be a point. Point mass particle का example. Am I part of the class? I am. So, point mass particle का example, guys. Anyone? No one. What do you understand by a point mass particle?
Very small dimension.
Compared to
Can you give me an example? Compared to?
जो हम measurement कर रहे हैं, like tennis
Compared
ball
to its trajectory, you can say, है ना? Compared to its trajectory, you can say, yeah. So या तो अगर हम real life में देखें तो mostly subatomic particles are point mass particles. Like for example, you can have an electron, you can have a neutrino, you can have quarks. So these are all point mass particles as far as we are concerned. But in Newtonian mechanics, point mass particle is an approximation when an object is irrelevant when we look at its trajectory. So the dimension of an object is negligible compared to its trajectory. So particle move कर रहा है तो उसका जो dimension है, it doesn't matter when we do an analysis of its trajectory. So for example, Earth is a point mass particle if we look at its motion around the sun. If we look at the motion of the Earth around the sun, compared to the size of its orbit, the Earth is so small that we can assume it to be a point mass particle. Even though it is not, even though it is very huge. Similarly, if we look at a ball and its projectile, we can think of it as a point mass particle. If we look at the motion of a pendulum, we can think of the bob as a point mass particle. So as long as by comparison, the dimension of a body is very small compared to the nature of its trajectory, and we can approximate a situation where its size and shape is immaterial to the calculations, then we can say that's a point mass particle. But it's not always the case. We always come up with situations where we talk about rigid bodies. So when we talk about rigid bodies, how is a rigid body different from a point mass particle? Well, the dimensions of the rigid body come into place, come into the calculations. There is a rigid body that has a certain shape, that has a certain volume, and then we need to take into account its orientation, the change in its orientation as it is undergoing some kind of a motion. So the orientation is important. The shape, size, center of mass is important. So therefore, we also need to sort of do the analysis with respect to systems of particles or rigid bodies. Okay, so let us do a little bit of that analysis. So let's suppose that we have a large number of point mass particles. Okay, so rigid body can be thought of as a collection of point mass particles, such that every single point mass particle have their own individual position vector compared to the origin of some external coordinate frame of reference. So let's suppose that we have mass m1, we have mass m2, and we have mass mj, let's suppose, and the position vectors are given by r1, r2, and let's suppose this is just a capital R. Okay, we'll come to that later on. rj, let's suppose rj. Okay, now if there are point mass particles, then what kind of interaction that the point mass particle be involved in, and what kind of forces the point mass particles can experience. So we can think of that as this system and external to that system. So whenever a particle is experiencing a force due to another particle within that system, we can call that as internal forces or internal interactions. Internal forces or internal interactions. And whenever a particle experiences a force due to something outside the system, we call it external interaction or external forces. Okay, so therefore, if I look at the forces experienced by some kind of a particle, let's suppose ith particle, m1, m2, m3, m4, ith or jth particle, jo bhi hai. If I look at the interactions due to some ith or jth particle, then first of all, I can say that this ith particle is experiencing some kind of an external force. And second of all, it is experiencing interaction due to all other particles in the system. So all other particles ka matlab hai, I can say f, ji, so all other particles j goes from 1 to n. Okay, so let's suppose there are, let's suppose there are two particles. So one is interacting with two is interacting with one. But if there are three particles, then one is interacting with two is interacting with three is interacting with one. Yes, if there are four particles, then one is interacting with 2 and 3 and 4, 2 is interacting with 4, 3, 1, 3 is interacted 1, 4, 2, 4 is interacting with 3, 2, 1. Are you understanding? The larger the number of particles, the number is the permutations and combinations possible. So therefore, this simply represents a summation of all the other particles and their interactions with this one individual particle whose forces we are studying. Are you following?
Yes, sir.
So external forces are the result of some external interaction, maybe gravity, maybe something else, we don't know, electromagnetic force. Internal forces are the result of the internal interactions that the particles are experiencing. So an ith particle is experiencing interactions with all the other particles out there. Right. Now I can say that this is zero. Can I say that this is zero?
Yes.
No, we cannot. So let's say that let's look at all the net force experienced by ith particle. Net forces experienced by ith particle in a system of particles. Okay. So net force experienced by ith particle is essentially net force experienced by the system. Net force experienced by the system. That's what we are interested in. We're interested in evolution of the system. So net force experienced by the system mein kya hoga? You look at all the forces experienced by all the particles, and this gives us a summation over I is equal to 1 to n fi external. Okay, and this gives us a summation over I is equal to 1 to n and j is equal to 1 to n and fji internal. So these are internal forces. So now the question is this equal to 0 and why? Or why not?
So if
Zero
the
becomes
ith particle is applying some force over j, then j must be applying that force back at I. So does that not cancel out?
That's what I'm saying. So it should be 0, no?
Right.
So internal forces always cancel out. So if you look at the
Right, sir.
interactions, Yeah. So internal forces are never responsible for the motion of a system, essentially. So if you look at these individual terms, let's suppose F11 plus F12 plus F13, okay, plus on and on with the Fn, okay, plus F1n, okay. Similarly, I can have F21 plus F22 plus F23 and on up to F2n. I can have F31 plus F32 plus F33 plus on up to F3n, and इस तरह से नीचे जाता रहेगा ये, ठीक है, as many number of particles are there. Now the question is, what does F11 mean? The interaction of a particle with itself. As based on the definition of interaction, what did I say? Lone forces don't exist. So a particle can never really interact with itself. Okay. A particle cannot interact with itself. So this is going to be 0. Yeah. F22 is going to be 0. Yeah. F33 is going to be 0. Yeah.
Yes, sir.
Yes, sir.
Physically speaking, there is no interaction that a particle can do with itself and then start moving because of that. Otherwise, the whole Newton's laws will break down. ऐसा तो नहीं होता ना, मैं अपने आप को उठा के जा रहा हूँ, है ना? That's not possible. I cannot exert a force on myself and then create motion. It always is with respect to something else. मैं ग्राउंड पे चल रहा हूँ, ग्राउंड को पुश करके मैं आगे बढ़ रहा हूँ. अगर मैं स्पेस पे हूँ, मेरे को स्पेस में हूँ, फ्री फ्रॉम एनी काइंड ऑफ ग्रेविटेशन इंटरेक्शन एनीथिंग, कोई ऑब्जेक्ट नहीं है, मेरे को यहाँ से वहाँ तक जाना, मैं जा नहीं पाऊंगा until unless I do something like push gas to the back side. मैं अपने आप को खींच के नहीं लेके जा सकता. Are you understanding? So that's not possible. So self interaction is not possible. Next, F12 और F21 का रिलेशनशिप क्या है? F12 और F21 का रिलेशनशिप ये है कि F12 is equal to minus F21 based on Newton's third law. So therefore this cancels out. So in essence, as you said, Pratham, Fij is equal to minus Fji. Because of that, this gets cancelled out and everything else gets cancelled out. All the terms gets cancelled out. So essentially this entire thing becomes equal to 0, which leads us to the conclusion that internal forces always cancel each other out. This is a very important property. Internal forces always cancel each other out. Internal forces always cancel each other out. If they did not, then it would violate the Newton's first law also. As a system, it can move because of internal interaction. It's not possible. So finally, the entire net force experienced by this. So this net force experienced by the system is equal to, one second,
The applied external force.
The applied external force. Okay. Summation over I is equal to 1 to n external forces. So whatever the external force is acting on every particle, let's suppose the gravity is acting on each and every particle, that is the net force. All right. So now applying the second law, applying Newton's second law, yeah.
Again, for the intrusion, but how do we take into the account the Stirling's heat engine over here? I mean, due to the temperature difference over there, it is able to produce motion.
Can you explain? I'm not really familiar with that engine.
Stirling's heat engine?
Yeah.
Just a second. I don't remember the.
Give me a general idea of the construction. What's happening?
So it's basically an engine where there's a cool cylinder and a hot cylinder, or a cool sink and hot sink, like we take in thermodynamics. And due to the temperature difference, the particles interact, and as they try to rush from one
there
point
are
to
wheels?
another. There are not wheels necessarily, but gears in some sense that.
तो motion कहाँ पे हो रहा है? Surface पे हो रहा है?
Surface पे नहीं
मोशन
सर,
मोशन हो रहा है?
सा उसका, हाँ जी, मोशन हो रहा है सर.
तो स्लाइडिंग मोशन है, रोलिंग मोशन, क्या मोशन हो रहा है?
लीनियर मोशन. सर गियर रोटेट करता है तो उसको हम कौन सा रोटेटरी मोशन लेंगे?
गियर रोटेट करता है तो वो गियर किसी व्हील के साथ जुड़ा हुआ है?
ये सर उसको आगे फर्दर कनेक्ट कर सकते हैं, एक शाफ्ट के थ्रू आगे कनेक्ट होता है.
तो गियर व्हील के साथ रोटेट कर रहा है तो एक सरफेस है यहाँ पे.
Yes, sir.
एंड सरफेस में फ्रिक्शन है यहाँ पे.
Yes, sir.
तो हो गया ना.
अच्छा.
It is moving because it's जैसे anything else is moving. Just like I am walking on the surface of the ground, I'm pushing the ground backwards because of friction is going forward. If I take that engine and I leave it in space, will it be able to move forward? In the absence of a
surface के
ground.
साथ touch नहीं होता, but it has air inside it. Air के साथ contact में आ रहा है.
Okay, so you are saying that it pushes air outside?
Yes, sir. Yes.
That's a rocket system.
Yeah. So in
it's a rocket system. You are saying essentially.
In some sense, what's happening is the hot air is exiting. The cool air tries to rush in. So the hot air actually pushes the shaft upwards, and when it cools down, the shaft again falls back. And while the cool air is getting inside and again getting heated up, the entire cycle repeats itself over and over again, thus pushing the shaft back and forth and generating a motion.
No, I don't want to go into the details. Are you saying that this violates the internal forces cancel each other out kind of principle? I don't think so. Because there is either some kind of a mechanism of a rotation with respect to ground that is happening, and then it is pushing the ground backwards and moving forwards, or it is taking in some kind of air inside and pushing back. Some sort of a rocket system is there, where masses are being exited outside, which doesn't violate this.
It's
this
the latter.
concept.
Yeah, I thought it would violate. Yeah, it's the latter, but it doesn't violate.
It doesn't violate. No, that's a rocket system. You push something backwards, you move forwards. Okay, but then you lose mass in the process. So there is so the center of mass remains the same. Are you seeing? So yeah, there are two particles. One particle, you throw the particles this side, then you'll automatically move this side. If you are in space and you have a huge ball, just throw the ball one side, you will go the other side. That same phenomenon as conservation of linear momentum. So that doesn't violate this idea because ultimately the center of mass remains the same. Okay?
Right, sir. Thank you.
So applying Newton's second law, we end up getting that F net is equal to summation of all the forces, all the external forces involved, and one force can be written as Fi can be written as, you know, d up 2 upon dt2 of mi/ri. Yeah, this is one. So F net यहाँ पे हम लिख सकते हैं d2 upon dt2 of summation of mi/ri. ये लिख सकते हैं. All right. इसके जगह पे, because this is a summation of all individual forces, individual external forces acting on each individual point masses 1 2 3 4 up to n. So एक individual force एक individual particle के ऊपर लग के उसका individual trajectory determine करेगा, but because there is a summation, मैंने यहाँ summation को यहाँ लिख दिया. ठीक है, यहाँ तक clear है?
Yes, sir.
So now if I define some kind of a average, weighted average of all the positions, because there is R1, there is R2, there is R3 for all the n masses. So if I create a weighted average, if I created a weighted average defined as summation over mi/ri upon summation over mi, then this mi is not in total mass, mr is equal to summation over mi/ri, and then if I bring it here, so this simply becomes d2 upon dt2 mr. If the mass does not change, if m does not change during the course of its motion, this simply becomes F net is equal to m d2r upon dt2. This is the Newton's second law for a system of particles. This is Newton's second law for a system of particles, where m is the total mass of the system and r is some kind of a trajectory. R is some kind of a trajectory which is the weighted average of all the trajectories of all the particles in that system involved. And this is given a very special name which is known as, yeah,
center of mass.
It's called center of mass. Very good. center of mass. So essentially जब हम system of particles को study करते हैं, then we do not get to know about the individuals and trajectories of the particles, but we end up getting to know about the trajectory of this hypothetical position, which is known as the center of mass. So whenever we apply the Newton's second law to systems of particles, we end up getting the evolution of the center of mass and its trajectory. Okay, and with respect to the center of mass, we can figure out everything else. We can figure out what's the velocity of the center of mass, what is the momentum of the system. So momentum of the system can be found out from, you know, md r upon dt and on. So all those analysis is possible. Okay, so that way it was not evident that the Newton's second law, if valid for point mass particles, should also be valid for systems of particles, but in fact it is. Okay, I have shown the Newton's second law is valid for point mass particle. It's valid for rotations. We have a rotational analog of Newton's second law, and it's also valid for systems of particles. But it's just that the solution of the Newton's second law is RT, which is the trajectory of the center of mass, and not the individual point masses. But we can find out the individual point masses and how they are related to R separately if we are interested in that. Is that clear, guys?
Yes, sir.
Yes, sir.
Yes.
All right. There are two further points that I wanted to discuss, but I don't have the time and I don't want to continue this discussion in the next class. I want to go to the next topic. So I'll give it to you as a homework. You try this. Just try to prove conservation of linear momentum for systems of particles. Okay, systems of particles, not a point mass particle. Try to prove conservation of angular momentum for systems of particles. Can you do that? Can you try at least?
Absolutely, sir.
Yes, sir.
Conservation of linear momentum is not that difficult. It's very easy, but conservation of angular momentum for systems of particles is slightly tricky, so you'll have to look into it. Okay, what about conservation of mechanical energy? Is conservation of mechanical energy valid for systems of particles? Is conservation of mechanical energy, is it?
Okay.
Are you sure?
Yes, sir.
Well, that's a little bit of a difficult topic because it goes back to what Pratham was asking at the initial phase of the class about the formation. Okay, so conservation of energy for conservation of mechanical energy, okay, energy nahi, mechanical energy is a little bit of a tricky thing. It's not always valid because when systems of particles are concerned, we have to talk about the internal energy of the system, you know, heat, etc. etc. तो बहुत बार क्या होता है systems of particles में heat आ जाता है and internal energy आ जाता है, and because of their relative motion of the individual particles, the object may get heated up, or the system may get heated up, the internal energy may change, and that would violate the conservation of mechanical energy principle because that doesn't include other things. So we'll have to keep in mind that there is no change in heat, there is no change in internal energy, tab ja karke conservation of energy will be valid for a system of particles, otherwise they won't be. So it's not something that is easy to prove. It's a little bit of a complicated discussion. Okay.
So we can take into account that it is not conserved when we consider the system of particles.
See, I said mechanical energy, okay? It should not be confused with energy. Energy is always conserved. Mechanical energy simply talks about kinetic and potential energy. So they may not be conserved whenever we talk about systems of particles because there may be dissipation into heat and changes in the internal energy of the system itself. So if the system evolves in such a manner that the internal energy of the system changes, then conservation of mechanical energy will not be valid. But if I say that the system evolves in such a manner that the internal energy does not change, then the conservation of mechanical energy will be valid. Okay, because in point mass particles there is no such thing as internal energy, but when systems of particles come together, then internal energy, etc., etc., many things come into the picture.
Okay, sir.
All right, let me download the attendance and then I'll call it a day.